Well, almost simple at first glance, right? Like a kid's what if.
Yeah, exactly.
But then they just unravel into these huge, um, really profound puzzles in physics.
Absolutely.
So today we're asking one of those. What actually happens if you could shrink a photon's wavelength down, down, down to the absolute smallest conceivable limit? I mean, the Planck length.
Oof, yeah, that one.
It sounds hypothetical, maybe, but
Yeah.
asking that question throws us head first into this major clash
The real collision course.
between the two giants of 20th century physics.
Right.
General relativity, gravity, the cosmos,
Right, the big stuff.
and quantum mechanics,
Yeah.
like the weird world of super small atoms, particles.
A tiny stuff.
And at this extreme scale, this Planck scale, they just don't agree. We hit a wall, a really deep paradox.
It's true. Our current laws just, well, they break down. So our mission today in this deep dive is to unpack why that happens. Why does physics fail there? And then we'll look at the leading ideas trying to fix it. String theory and loop quantum gravity. They offer a radically different picture.
Maybe different visions.
Totally. We've sort of boiled down insights from a lot of detailed research, the notes on this, to give you a clearer path to understanding what's happening at the very edge.
All right, let's set the scene then. To really get this paradox, we have to start with the basics. Light, the photon.
The particle of light, yeah.
Now, we know its energy is tied to its wavelength. The Planck-Einstein relation tells us that.
E equals h nu, or E equals h nu, or E equals hc over lambda if you use wavelength.
Right. And the crucial part is that inverse relationship. As the wavelengths get shorter,
Its energy goes up, way up.
it skyrockets. It's not just a gentle rise. It's an incredible concentration of energy in a smaller space, like packing a tsunami into a teacup.
And that skyrocketing energy leads us straight to the Planck units. These aren't just numbers someone picked. They come directly from the fundamental constants of nature. C, the speed of light. G, the gravitational constant, the Planck constant.
The bedrock constants.
Exactly. They define the scale where quantum effects and gravity become equally important, inseparable. And that's precisely where our current theories are expected to fail, where things get really wild.
And the most famous of these is probably the Planck length, right? About 1.6 times 10 to the minus 35 meters. Just mind-bogglingly small.
Unimaginably small. People sometimes think of it like the universe's pixel size.
Yeah, I've heard that, like little blocks of space.
Right, but the deeper idea from what we've looked at is more subtle. It's not necessarily pixels, but the scale where our usual ideas of distance, of smooth geometry, just dissolve.
They break down.
Yeah, into something maybe like space-time foam. It's thought to be the shortest distance we could ever physically measure. Below that, space as we know it might not even, mean anything.
Okay, and then there's the Planck energy.
Right, which is huge, about 1.2 times 10 to the 19 GeV, or nearly 2 billion joules.
Which sounds abstract, but you mentioned it's like,
It's roughly the chemical energy in a full tank of gasoline.
wow, for a single particle.
For one elementary particle, yeah. But concentrated down at that Planck scale. And you see this across all the Planck units. Time, mass, temperature, they all point to these extreme natural limits where our physics runs out of steam.
Okay, so we have the superenergetic photon. Now bring in the other pillar. General relativity. Einstein's theory.
Gravity as curved spacetime.
Exactly. Gravity isn't a force pulling things. It's the shape of space-time itself being warped by mass and energy. And here's the key link. EMC2. Mass energy equivalence. Our photon has zero rest mass, sure.
But it has energy. Immense energy.
Which means it has an equivalent relativistic mass. And that mass, according to GR,
creates gravity. It warps space-time just like any other mass would.
So this hyperenergetic photon has its own gravity, which leads us to
the Schwarzschild radius, the point of no return.
Right. The critical size where if you compress something smaller than that radius for its mass, its gravity becomes so strong that nothing, not even light, can escape.
It collapses into a black hole, inevitably.
Okay. We have the pieces. The superenergetic short-wavelength photon, gravity as curved spacetime, the Schwarzschild radius. Now for the thought experiment. The Kugelblitz catastrophe.
Let's do it. Imagine we could create a photon with a wavelength exactly equal to the Planck length.
The ultimate gamma ray.
Pretty much. So we calculate its energy. It carries precisely the Planck energy.
That gasoline tank's worth of energy.
Exactly. And that energy means it has the equivalent mass, the Planck mass, which is tiny in everyday terms, about 22 micrograms, like a flea's egg.
Huh. A flea's egg. Seems small.
It is. But the crucial point is it's concentrated within a region the size of the Planck length. That's insane density.
Right, okay. So Planck energy, Planck mass, crammed into a Planck length space. Now apply general relativity. What's the Schwarzschild radius for that Planck mass?
And this is where it all blows up. You calculated R equals 2gm over c squared.
And the answer is?
The Schwarzschild radius for the Planck mass is exactly 2 times the Planck length.
Wait, say that again?
The Schwarzschild radius is 2 LP, twice the Planck length.
So, the radius where it becomes a black hole is larger than the space the photon itself occupies.
Precisely. That's the paradox. To even see or probe the Planck scale, LP, you need a photon with a wavelength no bigger than LP.
Which has Planck energy and Planck mass localized to LP.
But its own event horizon, its Schwarzschild radius, is twice that size, 2 LP.
So the moment you try to observe the Planck scale,
A probe itself collapses into a black hole. The photon is instantly trapped within its own event horizon.
wow.
The very act of measurement creates a condition where measurement is impossible. Any information it might have gathered is sealed off. And if you tried an even more energetic photon...
It would just make a bigger black hole, right? Because more mass means a larger Schwarzschild radius.
Exactly. You're just digging the hole deeper,
Yeah.
literally.
So the core conflict here, it's like quantum mechanics, making the photon, clashes directly with general relativity. It's gravitational consequence.
It's fundamental. A local quantum event has this unavoidable, non-local gravitational effect, the event horizon. The distinction between your probe and the space-time you're probing just vanishes.
It completely breaks down. That's
Yeah.
the wall. Physics, as we know, it just hits a dead end.
So, yeah. How do we get past this? This is where the candidate theories for quantum gravity come in, like string theory.
Okay, string theory.
Yeah.
How does it approach this mess?
String theory offers a truly radical fix. It says the whole paradox comes from assuming particles are points, zero-dimensional dots.
This is a standard model view.
Right. String theory says no, fundamental entities aren't points. They're tiny, one-dimensional vibrating strings. And that changes everything about photons and black holes.
Okay, so this universe of fuzz, as some call it, let's break that down. Fundamental strings.
Yeah, the idea is that all the different particles we see, electrons, quarks, photons, are just different ways these tiny strings can vibrate, like different notes on a violin string.
And gravity.
Gravity isn't tacked on. A specific vibration mode of a closed loop of string is the graviton, the particle that carries gravity. It's built in.
Which is elegant, but it needs extra dimensions, doesn't it?
It does, typically 10 space-time dimensions for consistency. But the idea is the extra ones are curled up, compactified, incredibly small down at the Planck scale. We just don't see them.
Like looking at a thin wire from far away looks 1D, but up close it's 2D.
Exactly. And there are also D-branes, these higher dimensional surfaces where open strings can end.
Okay, strings, extra dimensions, brains.
Yeah.
How does this solve the black hole paradox, the Kugelblitz?
It leads to the fuzzball hypothesis. Instead of a singularity, that point of infinite density.
Which GR predicts.
Right. String theory suggests black holes are fuzzballs, dense, tangled messes of strings and branes. Think of a ball of yarn, but quantum and incredibly dense.
So no singularity.
No singularity. Fuzzballs have a real physical size, a non-zero volume, and a kind of fuzzy surface. That immediately gets rid of the infinite density problem.
And what about the information? Is it still lost?
No, that's key. The information isn't destroyed. It's stored in the incredibly complex ways the strings within the fuzzball are vibrating and configured. Like information in a book is stored in the patterns of ink.
Okay. And from far away.
From far away, its gravity looks just like a classical black hole. The differences only really show up if you could get close to that fuzzy surface where quantum string effects take over.
So back to our Planck photon. What happens to it in the fuzzball picture?
Well, the photon itself is a vibrating string. When it hits the fuzzball, it doesn't trigger some new collapse. It just gets absorbed. It merges into the complex tangle of strings already there. It becomes part of the fuzzball, like a raindrop hitting the
She
ocean.
just joins the collective.
Exactly. The paradox disappears because the assumptions that caused it point particles, singularities, are gone. Reality, in this view, is fundamentally stringy and extended.
Okay, that's one way out. A universe made of fuzz. Now what about the other main contender? Loop quantum gravity.
LQG. Yeah, it takes a completely different path. It doesn't really change the photon. Instead, it changes space-time.
How so?
LQG quantizes space-time itself. It says space isn't smooth and continuous at the bottom level. It's granular, discrete, made of fundamental atoms of space.
Atoms of space, wow.
Yeah. So at the Planck scale, space isn't like a smooth sheet. It's more like a mesh or woven from tiny, indivisible quantum loops or nodes.
And these are described by...
Mathematically, by things called spin networks. These describe the quantum states of geometry,
Yeah.
and they predict there's a smallest possible area, an area gap. You literally can't have an area smaller than a certain Planck scale value.
Like a minimum pixel size, but for area itself.
Kind of, yeah.
Yeah.
It's a fundamental discreteness. And a really important aspect of LQG is background independence, meaning spacetime isn't a fixed background, like a stage where physics happens. In LQG, spacetime emerges from the interactions of these quantum bits of geometry. The stage itself is part of the play, dynamically created.
That's a deep difference from string theory, which usually assumes a background spacetime.
It is. Very different philosophy. Now, how does this discrete spacetime deal with our collapsing photon?
Right, the Kugelblitz.
As the energy tries to curve spacetime down to a singularity, it hits this fundamental graininess. The discrete structure resists.
Resists how?
It creates a kind of quantum pressure, a powerful repulsion at Planck densities. It's purely a quantum gravity effect, not like any classical pressure. Think of it like, well, maybe like the Pauli exclusion principle stops electrons piling up, but this stops geometry from collapsing infinitely.
So it fights back against gravity.
Exactly. This quantum pressure halts the collapse before a singularity forms. Instead, you get this hyperdense but finite temporary object called a Planck star.
A Planck star.
Okay.
Temporary, you said.
Yeah, it's not the end state. OQG predicts that this immense quantum pressure eventually wins. It overwhelms gravity and causes the Planck star to bounce.
Bounce, the whole thing rebounds.
That's the idea. The theory suggests this bounce transforms the interior region, what would have been the black hole, into a white hole.
The white hole. The time reverse of a black hole. Stuff only comes out.
Exactly. An object from which things can only escape. Now, the really wild part is time dilation.
Gravity slowing time.
Extremely. For someone hypothetically inside this bouncing Planck star, the bounce might seem almost instantaneous, but for us, far away. Due to the intense gravity, it would look like it takes billions, maybe trillions of years.
So it seemed like a stable black hole evaporating slowly via Hawking radiation.
But underneath, according to LQG, there's this incredibly slow-motion quantum bounce happening, eventually releasing everything.
So in LQG, the paradox is solved because
the singularity never forms. The granular space-time stops it. And the information isn't lost forever. It's eventually released in the bounce, maybe disguised as Hawking radiation over eons. No information paradox.
Okay. Two very different solutions. String theory changes the particles to strings, making fuzzballs. LQG changes spacetime itself, making it grainy, leading to bounces.
That's the core distinction, yeah. String theory quantizes the stuff in spacetime. LQG quantizes spacetime itself. Background dependent versus background independent. It's a really deep split in how you view reality.
You could try to compare them quickly. GR gives us point particles, smooth space, singularities, inescapable horizons.
Right. String theory gives us strings, maybe emergent space, no singularities, fuzzy horizons, and the photon gets absorbed.
And then LQG.
LQG gives us spacetime atoms, discrete space, no singularities, temporary horizons, and the photon forms a Planck star that bounces back.
Totally different fates for that poor Planck photon in each picture.
Absolutely. And this whole line of thinking, it forces us up against another huge problem in physics.
The problem of time.
Right. Quantum mechanics treats time differently than general relativity.
Massively differently. In standard quantum mechanics, time is often just there, a background clock ticking away, absolute. But in GR, time is dynamic, it stretches, it squeezes, it's part of space-time.
And they don't mesh well, especially not here at the Planck scale.
Not at all. Some of the fundamental equations people work with in quantum gravity, like the Wheeler-DeWitt equation, they don't even have a T for time in them.
No time variable. How do you describe change?
That's the frozen formalism problem. It's like physics is stuck in a snapshot. Many believe the solution is that time isn't fundamental.
It emerges, like temperature from molecular motion.
Something like that, yeah. Maybe it emerges from quantum entanglement or some deeper process. Our whole conversation, using words like collapse and bounce, relies on a notion of time unfolding. But maybe at that fundamental level, time just isn't there in the way we assume.
Mind-bending. So this whole thought experiment, this Planck photon, it's way more than just a theoretical curiosity, isn't it? Oh, absolutely. It's a powerful conceptual tool. It really sharpens the focus on the deep differences between these leading theories of everything. It forces them to show their cards.
It reveals their core assumptions about reality.
Exactly. These theories aren't just tweaking equations, they're asking us to fundamentally rethink matter, space, and even time itself. They're guiding us toward the kind of new physics we need if we ever want to understand the Big Bang or what's truly inside a black hole.
So the final answer, still out there, one of the biggest unsolved problems.
For sure, a true frontier.
But the journey, the asking of these what-if questions, keeps pushing the boundaries and reshaping how we see the entire cosmos. Something for you, the listener, to think about. If time itself isn't fundamental, what does that even mean for cause and effect, for our perception of reality unfolding?